So, thank you very much for being here. I'm really proud that my tutorial was selected to present at PyCon, my favorite conference. So this is Pythonic APIs, and it's about how to leverage the Python data model to build idiomatic APIs. I presented a similar version of this tutorial at OSCON 2 weeks ago, but this has been enhanced with a section especially for you. So my name is Luciano Ramalho. I am currently a tech principal at ThoughtWorks in Brazil. We have offices in many countries, and I just love working there. I want to tell you that. And I'm pretty old. I've worked at several places, and this is the best company where I, not only for their technical expertise, but also because of the way they treat people in general. It's just awesome. I highly recommend. And so I'm the author of this book, and I'm really happy because not only is it selling well, which is nice, but even better, people seem to like it. It has very good reviews, and it's been translated to several different languages. And I love the translations they gave to the title in Russian. So it seems, according to Python, to Google Translate, because I don't know Russian, it means Python to the heights of excellence. Isn't that cool? Yeah. And the Chinese one is even cooler, smooth Python. That's awesome. Who here has read or started to read the book? All right, thank you guys. Wow, yeah, awesome. Yeah, it's kind of a long book, so here's a tip for you who haven't read it yet or haven't started. Consider that it's 5 books. In fact, if I was smarter commercially, I should have done like the guy that does those You Don't Know JS books for O'Reilly. He has like 6 different books, very thin ones, and that's what I should have done. So the book is divided in 6 parts. Part 1 is just 1 chapter, so read that. And then the other parts you can consider as different books that you will read if you're interested or not. So just skip around. Each part should be read in sequence, but the parts are pretty much independent, and they talk about very different subjects. So that's a tip. Consider it's 5 books. So a lot of most of the material here is from the book, but there's some insights that I had that I wish I had put in the book, but that was too late because I had them later, that I'm going to present to you, and I think which are a good and useful message about Pythonic APIs. So let's talk about consistency. So consistency is a relative concept, right? One of the things that I like most about Lego is not only that they're fun to play with, but I also think they are an amazing feat of design. So you learn good design. And one of the features, for instance, is that all of the measurements in the bricks are related in very smart ways. And one thing that really amazed me when I discovered was, you know those Duplo blocks for little kids that are twice as big? So the standard block, I don't know if you know that, but it actually can be attached to a Duplo block on top and on the bottom, which is really surprising, but it's just an example of how well designed those parts are to work together. And so this is the whole idea of this tutorial, because Python, I think, is also very well designed, and the parts go together in really interesting ways once you figure out some of the essential parts of that design. So one thing that bothers people, me for instance, when I came to Python, was the fact that len was not a method. So that seems kind of arbitrary, and but look at how those methods or properties are in Java. See? So, yeah, maybe the fact that len is a function is unexpected for us, coming from other languages, but it's actually consistent within the story of Python, and I will explain why that's a good design and what problem it solves. In Java, you have, for instance, the string class has a length method. The array type, which is not really a class in Java, has a length property, and array list, which is very similar to an array, has a size method that does the same thing, which is returning the number of elements in the array. Now, I think the third example there for Java is just a mistake. I don't understand what the justification would be for that. But the second example is not a mistake. It's a conscious design choice that the designers of Java made. So let's talk about that a little bit further. So the Zen of Python, one of the things that it says is that readability counts. Special cases aren't special enough to break the rules, although practicality beats purity, okay? So len is sort of a special case. So the reason why length is an attribute is because the array is not really a class, so it couldn't have a method. And the fact that it's like that is for performance considerations, right? The array is such a fundamental data structure that you want it to be really fast. And asking for the size of an array is also a very common task, and you want that to be fast, so you don't want to go over all the expense of doing a method call, which is, in object-oriented languages, is a dynamic mechanism because of polymorphism. And so that's why they did it like that. Now, so the reasoning behind len as a built-in function is related to that. Well, also, I found a quote by Guido van Rossum where he says that he also finds this more readable. And it saves one dot when typing. So it's one character shorter than the method syntax. But the most important thing is that for the built-in types, what happened is, and built-in types here also include types implemented in C, like, for instance, the arrays in NumPy and other extensions that are written in C. What happens is, when Python sees the len of x, Python checks to see what the type of x is, and if it's a built-in type, then there is a C structure that describes this type, and this C structure has a field with the number of items in it. So then it just returns that value. So in fact, this is much faster than calling a method. There's no attribute resolution, no polymorphism, because it's built in the way the language is implemented. Now, in order to make this special case not break the rules, we can implement in our Python classes a len method, which is what Python calls when your type is not a built-in type. So when Python says this, for a Python type, it calls this. So then with this fallback, we can have a consistent interface to our objects. And we don't give away performance. The performance you can achieve with C types. All right, so when you implement classes in Python, you can implement several special methods so that they can respond to built-in functions like len and abs, so that you can compare, right, one object to another, so that you can iterate. So this is an example of iteration, right? V1 is an instance of vector, and because it's iterable, we can build a list from its components like this. This is another example of iteration, right? On these types of unpacking assignments, the right-hand side can be any iterable object. And so this is another example of iteration. And let's see two examples of APIs that I find really Pythonic. Of course, the standard library has many Pythonic APIs, but not every module in the standard library is the best example of a Pythonic solution to that problem. And I'm going to show you two examples here. So first one is requests. Who uses requests, this library? Yay, yes. It's really high level, but also powerful, so it's not limited. It's simple, but not simplistic. And so this code snippet does that, outputs the status code, number 200, and the content type. And this is an example that is possibly, it is very biased. It's kind of old too. But Kenneth Wright, the author of requests, used this in his documentation to illustrate why requests is better than the urlib2 module from the Python 2 standard library. As you can see, to achieve that result, there's a lot more code here, a lot more objects involved, right? And it's biased today because the standard library has evolved, so it's not as hard as it was before to do this, but it's still a good example of a Pythonic, of contrasting something that is Pythonic with something that is not, written by a guy who, or this example was chosen by a guy who is well known for doing really nice APIs. So here are some things that make requests idiomatic Python. You don't need to instantiate multiple objects to configure a request. It comes with batteries included, meaning that the default configuration handles authentication, for instance, is not considered a special case. The result object, R here, has this status code attribute, so that you can get that value easily, instead of trying to figure out what a method name would be and calling that method. And again, the headers is implemented as a mapping, which is a natural data structure to do that, instead of having you use this arbitrarily named getHeader method. You can use this notation. And I actually haven't looked at the implementation of this, so I don't know if headers is really a dict, or it's a custom mapping type, because you can do your own custom mapping types that respond to this syntax too, right? So that's one example. Another example is PyTest. Who uses PyTest? Yay, yes. And who does testing otherwise? Nice, yeah. So some of you don't do testing, start with PyTest, okay? It's simpler and more powerful than the UNITTEST module from the standard library. So this is an example of a complete test module. As you can see, it doesn't import PyTest anywhere. It just follows the convention of having this test prefix to the function. And it uses the assert statement to check, instead of some arbitrary assert this or assert that method. And PyTest is also a more powerful test runner, meaning a program that is able to find tests in your code base and run them, than the test runner that's part of UNITTEST. So this example here, I ran PyTest in the exercises directory of our example code, and you can see that it has found and ran tests in several modules, some of which are not even implemented using the, for instance, this one here uses the unit test framework to do, but PyTest knows how to handle that too. So you actually don't lose anything when you start using PyTest. If you already have a bunch of tests implemented in unit test, they will still be running, but you gain a lot of flexibility and also a nicer API. This is an example of the same test done with the unit test module. So not only you import unit test, but you also have to subclass this test case class, and then you have to use this assert, and the test runner only finds tests that are written with this particular syntax. So I think this is a very good demonstration of how a Pythonic API can be more pleasant, shorter. An interesting thing is, so it seems pretty obvious to use assert, the statement that we already have in the language, instead of methods like this. But there's a reason they use methods like this. Who knows what the reason is? Why not just use assert everywhere? Anybody knows? Anybody wants to guess? Sorry?
You don't want to break out too far. You want to keep going.
Oh yeah, that's one example. That's a very good reason. Yes, you want to handle this in some way, right? So the thing is, the PyTest runner handles that for you. And there's another reason. The other reason is that the assert statement, as it is, doesn't provide a good diff, for instance, of what was expected and what you got. So the way the failures are presented is not as useful for testing. But when you use assert and in a test that's run with PyTest, then PyTest also does that. So PyTest uses a lot of advanced metaprogramming to inspect. So when an assertion fails, it will inspect the frames in the stack, and we'll find out where the error happened and inspect the code around that error to present a nice diff of the failure. See, so it's an example of using advanced language features to make the programmer's life easier. Okay? So what are some of the idiomatic traits of PyTest? You don't need to subclass anything to create a test, but you can also organize your tests in classes, not only subclasses of UNITTEST test case, but also classes of with other structures. In the simplest case, the test cases are just functions, which saves a lot of boilerplate. You don't need to import PyTest in simple cases like this, and you use the assert keyword, like I said. But here's another example using PyTest, a more realistic example, because that one is really simple. In this case, I do import PyTest for two reasons. First, because I'm using this decorator here, and second, because I'm using this context manager here. So this decorator, I think, is one of the great ideas of PyTest, because it's the way that you set up fixtures. So a fixture is basically a function that is decorated like that, and the name of the function is important. Why? Because any test that takes an argument with that name will be given that fixture to run, which is really nice because it makes explicit the coupling between fixtures and the tests that really need them, right? In the test case framework, you can have the fixtures are attributes of the test case, and you can have bunches of them. So they are all in the scope of the test case instance when it's running, and it's not so explicit which tests need each fixture. You have to actually read the body of the text to see which fixtures are needed for the test. So this solution here makes refactoring easier because it makes this coupling more explicit, right? And the PyTest raises is just there's a similar thing in the UNITTEST framework too. This is just a context manager to see, that you use to see if this should raise this error. And this assert really is not necessary. If I'm just interested in checking that this statement raises that error, those 2 lines would be enough. However, if I do want to know if there's, for instance, something written in the exception message, then I can do an assert after that. Okay, so I really encourage you to go out and study PyTest if you're not using it, because I think you're going to be much happier with it. There's also Nose, is another framework, but I think PyTest is more complete, more robust than Nose. PyTest really needs to be awesome, because PyTest is used to test the PyPy interpreter, the Python and Python interpreter, which is a huge project. And so that's what they developed PyTest for that project. So, so this is one set of tips that I wish I had included in the book, but didn't. So Pythonic APIs usually don't force you to write boilerplate code. They provide ready-to-use functions and objects. It's very common in the standard library to see that pattern of, okay, so there's this class that you can use to configure an object to do something, but there is a ready-to-use instance. And sometimes they expose methods of that instance as top-level functions in the module, so that you can just call these functions without knowing that there's actually a class involved. So for the simpler case, that works very well. So Pythonic APIs don't force you to subclass unless there's a very good reason to do that. You know, I've been more and more convinced that subclassing is something that should only be done by framework authors, not users of frameworks. So they include batteries, so they make easy tasks easy, and they are simple but not simplistic, so they make hard tasks possible. One plugin that PyTest has allows you to run your tests in parallel on a network, and it's really amazing. You can do that in the office late. You only have to get the agreement of your colleagues to have a key installed for their machines, and this PyTest add-on actually connects to the other machine, sets up an environment to run the tests, and then erases the environment so the machine is clean. And so you can do that to run, you know, real functional tests without the problem of, well, with the performance of many machines. And finally, they leverage the Python data model to provide objects that behave as you expect and avoid boilerplate through introspection, which the Java community calls reflection. We call that introspection, and metaprogramming. Okay? So, any questions about these examples or comments? Okay, so let's talk about the Python data model. The Python data model is Python's object model, and that's something that I struggled a little bit, this terminology, when I was writing the book, because the Python books that I admire, like Python in a Nutshell by Alex Martelli, and now there's a new edition coming out also with Anna Ravenscraft and Steve Holden. They call this the Python object model. And so does Dave Beasley, whose books I always love too. He calls the object model. But the documentation refers to it as the data model. And I decided to stick to that terminology to encourage people to go read about the data model in the documentation. So, what is an object model? So object models are interfaces, standard interfaces and protocols for objects that represent language constructs. So if your language treats functions as objects, like Python does, so that means those objects have an API, right? So they have attributes and methods that you can call. The same with classes, right? So classes in Python are first-class objects, meaning you can pass classes as arguments. You can dynamically invoke classes in runtime. You can even dynamically create classes in runtime. And frameworks like Django do that all the time. But the first time this whole notion was formally discussed in a book, I think, was with that book, which has this wonderful title, The Art of the Meta-Object Protocol, and an awesome cover too. And what's the story of this book? This book was written by people who were involved in the process of creating a standard way of doing object-oriented programming in the Lisp language. So Lisp, as you know, is extremely powerful and flexible, and when it was created, there was no talk of object-oriented programming. But when object-oriented programming started to get an attention after Smalltalk, the people, different groups in the Lisp community started creating their own object-oriented extensions. So that contributed to the problem of having multiple dialects of Lisp coexisting. But so as part of the common Lisp standard, they decided to adopt a standard way of doing objects, and this book discusses that. So it's very interesting because it's a book that presents alternatives and discusses design choices in handling functions as objects or classes as objects and so on. The APIs in the Python data model use special methods and attributes named with this double underscore syntax, which some people in the community call the dunder syntax for double underscore. So when I say dunderlen, this is what I mean, okay? Instead of saying underscore, underscore, len, underscore, underscore. So the dunder word is useful, shorthand. And an interesting thing about special methods is that they are designed to be invoked by the Python interpreter and not by your code, okay? So it's an example of what people call the Hollywood principle, right? It's the same thing that happens when you are using a framework. Usually when you're using a framework, you implement functions or methods that are called by the framework, right? Like for instance, in a Django environment, you don't usually call your view functions, right? They are called by the machinery of the framework. So that's the idea. And in particular, let me address a question that somebody asked me once, is, so if I have an object x, is it faster to call the len of x, or x dunder len open close paren? The first alternative is always faster. It may, for a built-in object, certainly, because of that fact that I mentioned. And, well, the second alternative perhaps is actually faster to spell it out. The second alternative meaning if x is a built-in object that you created. But because the main overhead there of this call is actually the method resolution, then it's going to be expensive anyway, because you're going to fall down to that. So then in that case, I think you should always use the len of x and never call dunder len directly. Sometimes when you're doing advanced metaprogramming, you do need to call special methods explicitly, but that's rare. And I will not do this in any example here. So when does the interpreter call those special methods? To do many things. It does that to do operator overloading. So when you use your objects in arithmetic and Boolean expressions, when you do implicit conversion to a string, like when you do the print of x, you get the stir method is called. Conversion to Boolean in Boolean contexts, like in those statements. So if you say while x, Python will use a special method to determine whether x is true or false. Attribute access with the dot notation. Emulating collections like sequences or mappings where you access items with the brackets. The in operator, like k in O, also uses special methods. The len of O also. Iteration, even some cases like, for instance, star arguments, when you call a function like that, f of the star of x, this iterates over x with blocks, so context managers. To implement your own context manager, you need to implement special methods. And metaprogramming, like descriptors and metaclasses, which are advanced topics that we won't be able to address here. So let's do a first example, which also becomes then an extension of this example becomes our first exercise. So we're going to do a class to represent vectors, Euclidean vectors, like those we learned in math in high school. So for instance, here we have this vector is v1, this other vector is v2, and this is the result of the addition of v1 and v2. Basically, you add the components. So 2 plus 2 is 4, 4 plus 1 is 5. Okay? And if you wanna, soon we are going to do the exercise. So if you wanna go to those places, those point to the same place. So Fluent Python is the GitHub organization where I put the book examples and other examples related to the book, like for this tutorial. And yeah, that short link also goes there. All right, so let's talk about this first implementation, the version 0 of Vector. This doesn't support addition yet, but it supports some basic operations. So let me explain how this works. So the way this is constructed means that the component's argument can be any iterable, right? Because, and here's a tip. For instance, often you see code that does this. Okay, so to call this function or method, you have to pass a list of something, okay? And then you see in the init method something like self.mylist equals the list that was passed as argument, okay? This is usually a bad idea, not always, but most of the time is a bad idea. And why is that? Does anybody know? Why assigning, imagine instead of coding this like this, I could have done self under components equals components. This would actually work for most of the examples that I have in the tests, but it's a bad idea. Who knows why? Sorry? Yes, exactly. So because lists are mutable, it's often a bad idea to share a list like that. The person who is passing you a list, maybe she doesn't expect you to change the list or manipulate it in any way. So it's better that you create a copy of that for your own use, okay? Unless you need to do some optimization. But as you know, premature optimization is the root of all evil, right? So the optimization would be, okay, but I have 10 million items in this list, I don't want to copy them. This is an optimization. In the standard case, usually what you should do is copy the thing. And the second advantage, and the way I copy it, if it was a list that I needed, I would do list of contents, right? So this is a way of making a copy of a list, but it's more flexible because the list of X can build a list from any X that is a finite iterable. So you don't force the person to pass the list. You're building a list from the iterable, okay? In this example here, I'm using array because it makes sense. And one of the ideas of my book is to show why some things are the way they are in the standard library. And so why do we have an array class when lists work pretty well? Who knows? I can do a list of floats as well as I can do an array of floats, right? What's the advantage of doing an array of floats? Sorry? Yes, that's one advantage. If you want to make sure, like we do in this case, that the iterable passed as the component's argument is made of numbers that can be converted to float, this takes care of that. Another advantage is that the array is an array of 10 million floats is just one object, while a list of 10 million floats is 10 million and one object. You have 10 million float objects, each with their own struct describing besides the bits that actually make up the float, and there is the list object that refers to them all. But the array data structure in Python is as efficient as the array data structure in C. It's just just packed bytes, one after the other, with the floats in there, or integers, or whatever, right? So if you do a lot of, if you manipulate lots of numbers, do use array instead of lists. It saves memory and it's faster, and also enforces types. Okay, so now we have the components array. So the len, what I do is to implement len of a vector, I just delegate to the len of components. The iter method. So the dunder iter method is to implement something that is iterable. And so the dunder iter method should return an iterator. There are several ways of doing that, but one way is calling the iter built-in function on an object, and this will return an iterator. So notice this pattern is the same. I have a dunder method, and what I do to implement it is I just delegate a built-in function of, in this case, the same name to this inner object here. So it's an example of using composition to implement functionality and delegation. So the abs. So the abs is to support the abs built-in function. The abs built-in function returns the absolute value of a number. For the built-in type complex, it returns the modulus, right, which is using the Pythagorean formula. And this is an implementation of the Pythagorean formula using a feature that I like a lot and that you're going to see a lot of my code, which are generator expressions, right? So who is familiar with this syntax? All right, most of you. Excellent, yes. So many years ago, I was at a training class at a company, and Guido was invited to give a little talk at the class, and somebody asked him, which features of Python were copied from other languages? And he gave a very humble answer. He said, everything that's great about Python I copied from other languages. And for instance, this syntax was copied from Haskell. And actually, I think it was proposed by Raymond Hettinger and not by Guido, but it's awesome. So, so I have here the sum of the squares for all x's in self. Notice how I am not reaching into the components thing. So this is not tightly coupled to the representation of the data structure. I'm leveraging the fact that self, which is an instance of vector, is iterable, right? Would it be faster to just reach into the components? A little bit faster, yes, but then you would have tighter coupling between those parts of the program. So I avoid doing that. And here's a simple and kind of actually too simple, simplistic implementation of the dunder AQ operator, which is the comparison operator. And in the book, I actually work more on this example later, but this was how I started developing this. And I find it useful to have just a simple EQ implementation just to get started, so to make testing easier, right? Because, yes?
What are the underlying mechanics that you iterate over self? The self refers to the instance of the object itself, right?
Yeah, so what was the question?
What are the underlying mechanics that let you iterate over self?
Okay, so it's the fact that self is an instance of vector, and the vector class implements dunder iter. Okay, so any class that implements correctly dunder iter is iterable. So you can use it in contexts like that, all right? And like I said, there's other ways of doing it. This is kind of cheating because I'm delegating to the array and taking advantage of the fact that the array itself is also iterable. But if I had some very custom data structure, and I do present several examples of that in the book, this would probably be a generator function. You know, to use using yield, because a generator function produces a generator, which is what the dunder iter method has to return. Okay? Thanks for that question. And people, please ask questions. The workshop goes much better if people ask questions. Okay? All right. So, okay, so with this code, we can do all of those operations that I had shown previously in another slide. Okay, so here's another thing. What I'm doing here is, first of all, there are some a little Pythonic trick here, because this is a long expression. I put it between parentheses so that I can continue in the next line without using that awful backward slash at the end, which is kind of dangerous because if there's a space after it, then you're done for, right? So don't use that, put parentheses, yes?
Is there a reason you chose having components just be a list and not bare args? So that,
yeah, that's a good question. Yeah, so I could have written star components, right? So that I could instantiate vector by passing individual arguments. I actually did implement that way, and then I kept going back and forth. I think this is better because it avoids an unnecessary iteration over the arguments. In what example? If a person already has an iterable, then the person will have to explode the iterable with the star when calling this. And this will create another iterator, which, yeah, I think it's, and also I mimicked the several of the built-in functions that Python has work like that. And this is another tip for doing Pythonic APIs. If you are in doubt, take a look at how the standard library works in some regard. Like, for instance, every collection that I remember that is built from an iterable accepts the iterable, a reference to the iterable and not the many arguments. Okay? Yes, another question? Okay, thank you for asking that. Okay, so this is something of the array class because of the way the array is organized, like I said, like packed bytes in memory. When you create an array, you need to tell Python how the numbers in the array are going to be represented in memory. So you have to pass this argument. So the constructor to array takes this mandatory first argument, which is a type code, which is a letter that says how the numbers are going to be represented, because they may be ints of different bit lengths, and they may be floats of different bit lengths as well. Okay? So in this case, I chose to do double precision floats. This is what the D here stands for. Okay? So, just to review what we just did, we implemented under len, under iter, which is to implement the iterable interface. And here's the thing, because in Python we use duck typing, it's a dynamic typed language. This means that implementing interfaces doesn't entail declaring explicitly that you're implementing that interface. You just go ahead and implement the methods that the interface requires, right? That's the way of doing it in Python. And it's also the way of doing it in the Go language. They had this idea, and Go, I think, is the first, at least that I know of, the first statically typed language, strongly typed and statically typed language that does that. You don't declare the interfaces that you implement, you just go ahead and implement them. And the compiler will check. It's interesting. So they invented something that I call static duck typing. I never thought that was possible, but it is. Anyway, so the abs implement the modulus. So see, this is an example of abs with a complex number in the standard library, and this is the abs of a vector. And the equality operator, yeah. So let's talk about text representations. So here's the thing. Every object-oriented programming language has a standard way of turning objects into strings, right? Like, for instance, in Java and many other languages, the object class from which everything else derives has a toString method, right? And what is that used for? Debugging, yes. That's actually the main use of toString, right? Debugging. However, there's another use, which is presenting information to end users, right? So if you want to render the object as, as a string to display, the problem is those two uses are often incompatible. Because for debugging, we need a precise representation of the object. And for presenting to end users, that precise representation is probably going to have too many details that are confusing to the end user. So that's why Python has two standard ways of turning arbitrary objects into strings. So one is the stir built-in function, and the other is the wrapper built-in function. And this is not something that was invented in Python either. I found this paper from '96, because it was published in '96 at an academic periodical, probably they had this idea probably 5 years before, until they wrote a paper. So this is from the Smalltalk community, and this guy is saying we actually need two methods to do that. One called print string, and the other called display string. And the print string would be for, and the definition is here is nice. Is print string displays the object the way the developers want to see it, and display string displays the object the way the user wants to see it, right? This is such a small detail, and it seems like, why are you wasting time with this? No, actually, for instance, when I have to work with JavaScript, one of the many things that annoys me about JavaScript is the fact that we don't have this. So, for instance, and people don't take seriously the fact that they need a nice debugging representation of the object. So it's difficult to inspect objects in JavaScript sometimes. Anyway, so the most fundamental one is actually this one. Because, okay, so this one is used for debugging and is used in the in the Python console, when you just type X and hit enter, you will see the wrapper of the X. If possible and useful, you should try and emulate the syntax to rebuild the object. So the string representation of the object should be something that you can copy and paste in the console to recreate that object. Does that make sense? Sometimes that's not the best option, or is not even possible, because, for instance, the object depends on external resources or things like that. But when feasible, it's a good idea. And the stir function calls the dunder stir method if you have implemented it. But if you haven't implemented it, you're going to be inheriting the dunder stir method from the object class, and that just delegates to dunder wrapper. So that's why dunder wrapper is more important. You should, in my opinion, you should always implement dunder wrapper, and then implement dunder stir if it's convenient or useful in your project. So here's an implementation of those two things, and that's in that example, vector v1. Just to show the result, because this is a little bit complicated, I want, and this is simple. Let me explain this first. So this, I'm using it when I do print v3. This is what I get. So I decided to make the user-friendly representation of a vector, just a bunch of numbers between parentheses, which is a way that mathematicians and engineers often represent vectors. Okay, so the way I did it was, very simple way, not very effective, but anyway, if the person wants to see a display of that. So what I did was I just I built a tuple from the self, and then I do a stir of that. Okay, that's very simple. And this is not so simple, but I did it this way here because I wanted to show you, or I wanted to talk about the wrapper lib. This also existed in Python 2, but it changed the name. The library was called wrapper in Python 2, and now it's wrapper lib, which is a better name. So the way it works is wrapper lib has a function called wrapper. And that function is smart in several ways. One of the ways that it's smart is, by default, if a collection has too many items for some definition of too many, it will just display the first ones and add an ellipsis, actually 3 dots at the end. So this is useful because if you have a vector with 10 million items, you probably don't want to see that in a log or when you're debugging, right? And this is handled automatically by the wrapper. By the wrapper function from the wrapper lib. Another thing that it handles, which is kind of tricky, is circular structures. Because it's possible in Python, for instance, to have a list that contains a reference to itself. And a naive implementation of the wrapper for that could fall into an infinite loop. But the wrapper lib can handle that. It knows when it's displaying the same thing again. So what I do is I use wrapper lib to get the wrapper of the components. And the wrapper of the components follows that rule of being a representation of the code you could use to reconstruct the array, which means it starts with the word array, and then open paren, and then there's a type code, a comma, and a bracket, and then a list of arguments within the brackets, and then close paren. So that's what this returns. And what I do here, I take a slice, see? This is a slice to retrieve only the part within the brackets, including the brackets. And then I built a string with that inside a call to vector, so that's this notation here, all right? Indexing and slicing. Okay, so indexing and slicing. If you want to support bracket notation to retrieve items in a collection, you implement dunderGetItem. And this method is kind of overloaded for several functions because it's the same method that is used in sequences where you retrieve items by an integer index, but it's also used in mappings where you retrieve items using some arbitrary key. And it's also used for slicing. Okay, so how does that work? The second argument, x here, that dunderGetItem gets, can be either an integer index, some arbitrary key, if you're implementing a mapping, or an instance of the slice type. So I said that Python is very consistent, but and it is, the semantics and the syntax of the language I find very consistent, but there is, the naming conventions of the language are kind of annoying, right? Because slice is a type, but it's not written with uppercase S, right? So, and I think the tradition is, as far as I understand it, is that it's very arbitrary. Things that are originally implemented in C in the language, those types have lowercase names. Well, this is kind of a bad, anyway, yeah, because actually things change. Sometimes things are initially implemented in Python and then they're re-implemented in C. But it's, yeah. So you have situations like, in the collections module, there are two variations of mapping, default dict and ordered dict. The first one is written all lowercase, and the second one is camel case. So go figure it, all right? Okay, so there's a slice type. And how does it work? Look at this, I created this little class with dunderGetItem just to display what the x is. So if I pass it an integer, you get the integer. If you pass this notation, then you get an instance of slice that looks like that. And if you use this notation with the step argument, then you get an instance of slice that looks like that. So the interpreter actually builds those slice objects for you when it parses this notation. So this is an implementation of dunderGetItem for our needs. And first what I do is I get a handle to the class of the object because I'm going to use it here. So to do that, I do the type of self, and this function returns a reference to the class of the object. And now I need to check what is the index. So if the index is an instance of slice, then I just do the old trick of delegating to the components array, because that also supports slicing. And then I use that slice of the array to build another vector. CLS here is our vector class. And this is the correct way of implementing slicing is to create copies of the elements, right? So I'm creating a new vector. The second example is if the index is an instance of an integer, but I used a kind of a fancy way of testing whether it's an integer, because instead I could have written int, but here's the thing. As I started to play with NumPy, I discovered that NumPy implements several other built-in numeric types, or actually several other numeric types implemented in C, such as integers with limited range and floats with different precisions. So if I want to support all of those numeric types correctly, at least the integer types, I should do this. So the numbers module in Python is it implements a hierarchy of numeric types where the topmost, I think it's called number, and then you have they are like the numeric sets in math. So you have complex numbers, you have numbers in general, and then you have complex numbers, and then you have real numbers as a subset of complex numbers. And I don't know if there's rational there, maybe, but there's also the integer, the integral type, which is a subclass of real. So a float won't pass this test, okay? But an integer of any kind, including the integers implemented in NumPy, should pass this test. So otherwise, if I got a string or a float or any other thing that is not a slice and not an integral, I just display an error message. And here's another tip about doing Pythonic APIs. Try to emulate the language used in the error messages. See how Python complains if you do something with some built-in type and emulate that message. You may be able actually to write a more informative message, but that's kind of risky because the other one may not be so informative, but it's one that people know. People are familiar with it. So that's what I did here. Okay. So I display the name of the class to say like vector indices must be integers. So this is what I'm doing there. And I raise a type error exception. So that's the functionality of our getItem. And an interesting thing is, because I am delegating to the array, I get some nice features like negative indices, which is something that I think every language should implement, right? Come on, people, get on with the program. This has been in Python for 20 years already, right? Yeah, it's such a simple idea, but it's very effective. Okay, so operator overloading. We're kind of late, but I wanted to show you this because I want to do the exercise. So, all right, so operator overloading is really great. It's something that is not in Java because James Gosling thought correctly that people abused it in C++. Yes? Mm-hmm. Okay. Well, I could do that here. I didn't know that, actually. I never tried that in NumPy. So you could usually, sorry, yeah, go ahead. Yeah, so you could do that here by just testing, instead of testing against numbers.integral, testing against numbers.real, and then that would also accept floats, and then you just would do the int of the index here, and it would work like you described. Yeah, well, yeah, so you would have, you could add some logic here to check that, yeah. Yeah, it doesn't make sense, 1.5 really doesn't make sense, yeah. Okay, so, but despite the fact that it was a feature that was abused, we shouldn't, throw the baby out with the bathwater, right? Let's just say, people calm down and don't overuse this, all right? Or whatever. So, because look at this. This is the compound interest formula in Python. And this a formula is very similar to this, also works in Java if you're using floats. But for instance, suppose you're doing banking, which is likely if you're working with interests. And then you need to have a precise representation of money values. So you're going to use a class like decimal that offers that. In Java, there's big decimal. However, because Java does not have operator overloading, when you're not using one of the standard built-in types, or primitive types, then you cannot use infix operators anymore, and your formulas start looking like that, which is really terrible, right? So it's probably one reason, Python is a big success these days, and probably one reason is the fact that it became very popular in science, and then those things that people did in science, like NumPy, SciPy, and all those other libraries, turned out to be extremely useful for doing big data analytics as well. So, but if we couldn't have this kind of notation in Python, the scientists wouldn't care about it, right? Because they don't want to write stuff like this. Their formulas are much more complicated than this. And they want to be able to multiply two matrices by saying A times B, or something like that, right? Anyway, so the way operator overloading works in Python is by implementing some special methods that have names like dunder-add and so on. And here's an implementation of scalar multiplication, which is how you multiply a vector by a scalar number. Okay? So what you get is a new vector that has the components multiplied by that scalar. Okay? And I can also use a fraction, for instance, which is another type that Python supports. And the way I do this is I check whether the scalar argument is an instance of numbers real. So floats, ints, fractions, all of them satisfy this test. And then I do a generator expression to multiply for each n component in self, I multiply that component by a scalar, and then I build a new vector with that. Otherwise, if the scalar argument is not what I expected, then this is a really important part, okay? What I do is I return not implemented. I don't raise an exception. And there is an exception called not implemented error, but this is not that. This is a special singleton object, just like none. So it's a special singleton object that was invented just to signify that a certain operator method doesn't know how to handle its operand. And why isn't it an exception? We are going to talk about that shortly. But, okay. So what I'm going to do is I'm going to do the break now because I don't want to be too late for the break. What time is, how much time do we have for the break? I don't know, actually. 10 a.m. here it says. We are already late. I hope there's still coffee. Let's see. 20 minutes, all right. Okay, so, yeah, all right. So we can be back in 15 minutes, okay? 10 minutes, okay? I don't know. Yeah, let's get started. Let's get back in 15 minutes, all right? So 10:25, all right? Thank you. So here's the thing. These tests pass with this implementation, okay? However, this test fails. So I can multiply a vector by 10, but I can't multiply 10 by a vector. Does that make sense? Yes, because 10 is an int. So Python is going to call the dunder-mul method in int. But that was created 20 years ago, so it doesn't know anything about vectors that we just invented. So it doesn't work. But it should work. So how do we make it work? And this is a beautiful, the solution to this problem is beautiful. It's something this is a coding pattern, double dispatch, that was also invented by the Smalltalk guys. But Python has built-in support for the mechanism, so that it's actually easier to do it in Python than it is to do it in Smalltalk. And the way it works is the interpreter checks whether, to evaluate A times B, it checks whether A has done their move. And yes, the int class has done their move. But then it calls A done their move B, and the integer class returns that special value not implemented. So then, since the result was that, Python goes and checks whether the B operand has an rmove method. And in our case, it doesn't. So then it raises type error. So that's why we don't raise an error. We return this special value so that we enable the double dispatch mechanism to operate. And so the two happy results here are when A implements done their move with B, and it does not return not implemented, then the return the value that we got is the result. Or when this returns not implemented, but the B has the rmove and it doesn't return not implemented, then we have the result. Does it make sense? Isn't this nice? This is awesome. It's a way of future-proofing operator overloading, right? So to solve this, in this case, it's very simple because of the commutative property of multiplication. V1 times 10 should produce the same result as 10 times V1. So the implementation just multiplies self by the scalar. And this will, in turn, invoke this, and we get the result. OK? So let's talk about, OK. Yeah, so this example returns a vector. The at operator is something that was introduced in Python 3.5 to fix a problem that I described. Actually, I mentioned before that I said, oh, so the people who do numeric programming, they want to be able to multiply two matrices by doing A times B. Actually, that was wrong, because they use the times operator to do scalar multiplication, like we are using it here. So they needed another operator to do matrix multiplication, right? And there was no operator available. And so because of the importance of Python in this numeric space, for the first time in many, many years, Python gained a new operator, which is the at operator in Python 3.5. And so that's intended for matrix multiplication, or in the case of vectors like we are using, it's a dot product, which is kind of a special subset case of matrix multiplication. So the idea is I have a vector here and another vector there, and the operation is to multiply the corresponding elements and then add the results together to produce a scalar result, right? So this is the math formula for doing that. It's interesting that the at operator was added in the standard library, or not in the standard library, but in the language, actually. But there is no part of the standard library so far that uses it. In this case, I have two vectors, and when I multiply them like that, this is the result that I want. So 1 times 5 plus 2 times 6 plus 3 times 7 is, and the sum of all of that, yeah, is 38. Okay. The way I implemented it uses duck typing. So actually, I can multiply any iterable of numbers to a vector, or vice versa. But I can't multiply a vector with a a scalar, because this would be just wrong, right? Okay, so this is how you implement it. There's the method, the special method assigned to that operator is called matmul for matrix multiplication. And the way I do it is, here's what I do. I try to do this. So, you know the zip function? And the zip function is one of those wonderful functions that exists in Python to support the fact that our for statement was designed to avoid us having to fiddle with indexes, right? We hate fiddling with indexes because we get off by 1 errors, right, when we do it. But for instance, a common case where you would need to fiddle with indexes is when you have to iterate over data structures in parallel, which is the case here. I have to iterate over self and the other vector. And so zip solves that very nicely by returning a generator that will yield, in this case, because there are 2 arguments, the iterator will yield pairs, tuples of 2 items with 1 element from each. So this makes the solution really nice. But there's things that can go wrong here. What can go wrong here? One thing that can go wrong is that the other is not uniterable. And if that happens, the zip will fail, and we will get a type error. And the other thing that may happen is maybe the other contains items that are not floats. And then again, we get a type error. But to play along the rules, I'm not going to raise type error. I'm going to catch that and return not implemented so that a person can implement in their own class something to support this operation. Okay? And again, the reverse operator. Some people, there's no clear definition of what this R stands for. There are different explanations in different parts of the standard documentation of Python. I prefer to call it the reverse special method because you have the forward special method and the reverse. So forward and reverse are nice opposites. Some people also call them the right special methods because they have to do with the right-hand side of the expression. I prefer the reverse. Anyway. And I also like the fact that this is a very nice notation to represent that, isn't it? You know, for elements A and B from for elements A1 and AI and BI, multiply them and sum. I think this is very beautiful. So let's do an exercise. This tutorial was designed to have a break in the middle. We're now in the middle, but we don't have a break, so it's okay. So let's do the exercise. The exercise is simple. You go to that place to get the repository, and then what you're going to do, there are instructions on this link here. This is not exactly the same destination as that. This is linking to a document inside there. But let me show you that. If the network cooperates. I was online previously, but now that I need it, I'm not. Anyway, so I also have a local copy of this, so let me show you the local copy. So this is the unrendered restructured text for that. I actually have the render too. Let me find it here. Okay, so this is how to do the exercise. You should have installed PyTest, and then if you run the test there with PyTest and the slash or -x option, let's do that. So I get an error. And that's the error that you need to fix. Okay, basically, we're going to implement the unary minus operator, which, given a vector, returns a new vector with the component values negated. Okay, so the exercise entails solving that. And you do that by editing the vector.py module to implement the dunder-neg method. Okay? And once you do that, this test should work. Yeah. And let's do this for 10 minutes, then I'm going to ask who is done. Feel free to pair up. You know, I work at ThoughtWorks where we do agile programming and we pair with everything. The marketing people pairs to do presentations. In Brazil, even our country manager is actually 2 people, 2 women who pair to be country managers. This works really well. And if you need help with anything, please call me. Oh yeah, and once you do that, there's actually another exercise, which is the vector addition. There's another test for that. And then that's where you implement the plus operator. Yes.
Question. So in get item, you did this. You created a class to just get that type.
Yeah.
But then in mul, you didn't. Is there like a when should you do it and when shouldn't you? Because I
Yeah.
can see this being kind of like a little
Yeah.
bit of boilerplate having to add it to every single method.
Yeah. Yeah, I was not very consistent there. I did it here mostly because I needed to get the name, and but I could also hard code the name like I did here.
Yeah.
So
True.
again, another inconsistency. So maybe I felt dirty when hard coding the name here, and then I decided to do that. Perhaps I should have done it like that elsewhere too. Yeah. Yeah. Thanks for pointing that out.
Oh yeah.
Did you solve the problem? No, not yet.
No, it comes on for a little bit, but then it hangs up, so I'm trying.
Yeah, right now I'm not even connected either, so I don't know if that's any consolation, but if you've done that, you can do another exercise that I just invented that's really easy to code, which is to implement the subtraction. Now that you already have the negation, you can just add the negation of the, add vector plus minus the other. That should do it. So it's going to be really easy to implement. But that's just for you who are bored because the exercise was too simple for you. think the special name for the subtraction is then there's sub. So, who is done? Some people are done. Who is still trying? No problem.
I'm trying your sub one.
Oh, okay. So I need to move on because of time. So the solution is actually in the exercises vector solution directory. It's very simple because it looks a lot like our multiplication. The way I did it was, in my case, I decided not to accept multiplying vectors that are of different lengths. In math, that wouldn't make sense. In practical applications, maybe it could make sense, but then you would have to fill up one of the shorter vector with zeros, for instance. That could be done. But so here, the first thing that I do is I test whether the len of the arguments differ, and if they do, I raise a value error. And this is a case where I don't return not implemented, right? And this is a very subtle difference, because I know how to do the operation, but the operation is not valid. It's different from I don't know how to do that. Does that make sense? So for instance, like division by 0, right? Okay, I know what you're trying to do, but that's just not valid. So I raise value error. Value error is usually the error you want to raise in cases like that. If I get a type error, on the other hand, this is something else. Maybe one of them is not readable or whatever. Then I return not implemented. And then I do this. I should probably wrap this around a try except clause also to return not implemented if this raises type error. Yeah.
So you would say it's reasonable to move that up
Yeah.
to the long chapter?
Yes. Yes. This could be inside here after the if. Yeah. Like this. Yeah. I think this is better. Also, sorry, what's your name? Matt. So Matt pointed out something that is an inconsistency in my coding style. Sorry about that, but we are all human. So the inconsistency is that I went through all this trouble of getting the class here, but in other places I just hard-coded the class, like here and here. So it is really an inconsistency in my coding style. I think, to be honest, what happened was perhaps when I wrote this, there were so many references to the vector here and hard-coded and so on that I felt dirty doing it, so I decided to do this way, which is better. But, so this is simpler. So I also like simple when it works. Okay, so let's So I'm going to skip this hashing part. It's a bonus section. If we have time, I will come back to it later. But this is now we are moving to an entirely different example and another take on the whole Pythonic API things, which doesn't always entail using special methods. There are other features of the language that you can use to do Pythonic APIs that don't have to do with special methods, but do have to do with the data model, with the fact that the objects in the language, the constructs in the language, like functions and modules, are classes, are objects and instances of classes, so you can use that to your advantage. So this is about rethinking the strategy pattern. Here's the thing. After studying design patterns for a while, I discovered a presentation, a 1996 presentation from Peter Norvig, the computer science professor at Stanford, who also works at Google. And he has, if you Google for Peter Norvig design patterns slides, it's very interesting, because in that presentation that's very old, he actually says that he was talking about Lisp and Dylan, which is similar to Lisp semantically. But he says that in dynamic languages, and Python is an example of a dynamic language, in dynamic languages, you have to rethink many of the original design patterns. So the original book has 23 design patterns, and he claims that you have to rethink 16 of them, I think, is the number he gives, okay? Because they were designed mostly to solve problems in C++, and they also solve problems in Java. So those patterns apply equally well in Java and C++. But some of them are much simpler to implement, or you don't even need to implement because they are built in the language when you're using a dynamic language. And this pattern here is an example of a pattern that even in Java today, with Java 8 and first-class functions, which is this new thing in Java 8, you should also rethink and do it the way we are going to do it. So what's the idea of the strategy design pattern? So that's the description from the book. It says, define a family of algorithms, encapsulate each one, and make them interchangeable. The strategy lets the algorithm vary independently from clients that use it. Whoops. Java is available. Excellent. That's just what I need right now. See, I invoked the beast and it came. So anyway, so all right. So what's the idea? The idea is that this is a concrete example. It's not the same example that's in the book, but I think this example is more familiar to many of us. And this is the terminology of the book in terms of the roles that those classes play in the pattern. So the pattern talks about a certain context, and the context will have a strategy, but the strategy is an abstract class. The italics here means abstract, which is basically just an interface. And then you have concrete implementations of that interface that implements a certain method that is used here. Okay, in the concrete example that I'm giving, you have an order, and when the order is created, it's created with information about the customer and the order, and also with a promotion. Okay, this is a critical part of understanding the pattern, is the fact that the selection of the strategy is not part of the pattern. The pattern describes a situation where when the context is created, a strategy is given to it, okay? And how that's done is outside of the scope of the pattern. So anyway, this order is created with a certain strategy. And how is the strategy used? So there is a method that computes the total cost of the order, and there is a method that computes the amount due. And the amount due is basically the total minus a discount. Okay? So this due method calls a discount method on the strategy to compute the discount. All right? So, what are the examples? So here's it's actually copied from a doc test that you will find in the module later. So I have these numbers here to help me refer to them. So anyway, on the number 1 line here, there I created a customer, and on the second line is another customer, and then I create a shopping cart fixture that has several line items. A shopping cart is just a list of line items here. And then when I build an order with that customer and that cart and passing an instance of the fidelity promo, this is what we get. Notice the wrapper, the string representation of the order doesn't follow that rule that I mentioned first, but it's a convenient exception to the rule because I wanted to show you some attributes of the order, in particular the total and the amount due. So that's why I deviated from the standard way of doing the representation. But I also point that out by putting angle brackets. So when the representation has angle brackets, then the programmer reading that knows that this is not the way to call this thing to build it. Does that make sense? So angle brackets is used for a special representation that is not syntactically like rebuilding the object. And this is much more useful than saying that it's an order instance located at some random part of memory, right? Okay, so in this example, Joe doesn't get a discount because we are using the fidelity promo, but Anne gets a discount because she has 1,100 fidelity points, so she qualifies to get a fidelity discount. This is another example. I have a banana cart, which is a cart that has lots of bananas. And then even Joe gets a discount in this case because there is a promotion called book item promo, which applies to items that have many, I don't remember how many. Anyway, items that have many, that have some large quantity get the book item promo. And this is another example. This is an order that's made of 10 items. Doesn't matter what the items are. But again, there's a promotion called large order promo that applies in this case. Okay? And it doesn't apply to the regular cart here. Okay? So these are some tests. So this is the way this is implemented if you follow the recipe from the design patterns book. So this is the context class, is our order. Like I said, it takes a promotion argument when it's constructed, and I just assign this to this instance attribute. And so the total here, this has a little optimization. I'm just showing you because sometimes I'm going to use this total several times. So what I did was, if the instance doesn't have under total, we don't say the under here, okay? Because the under is only for 2 underscores in front and in the back. So if the instance of order has under total attribute, then I'm going to, if it doesn't have, then I'm going to compute it. and then I return it. So if it already has, I just return it, okay? It's one way of performing this computation just once, assuming that the order is immutable, which it is. Okay, the discount. What I do is, the do method. If the promotion is none, the discount is 0, otherwise is whatever this method call will give me, okay? All right, so this is the context, and this is the strategy interface. So in Python 3, you can create abstract basic classes by subclassing ABC, which is a class from the ABC module. And you also mark those methods, the methods that are abstract, with this decorator abstract method. And because you have to provide something, but usually you don't need a body in an abstract method, people sometimes put pass. You have to put something there, right? You need to have a body to be syntactic valid. But I like to use docstrings for that, because it serves the purpose of the syntactic purpose of having a pass, but it's more informative than just saying pass. So it's a good use of docstring. And here the other classes have docstrings that explain the business logic and their different discount implementations. So they inherit from promotion. And yeah, so that's the way it's done. Now, instead of explaining how this would be done with functions, because it's not so hard to do and it's, I think, fun to do, I'm going to propose an exercise. So the exercise is, again, so you go to this other short URL if you can. If not, the description is inside docs, then exercise 2. And in this example, I'm using doctest to test. Okay, so let me show you how that works. So if I run this, here's how I run it, right? So Python 3 minus m doc test. One thing that somebody should do would be a great contribution to the community is to document in a list, in a single place, all the modules of the standard library that can be run with -m and that provide useful services. I don't know if you know that, but there's this nice way of invoking a module as a script. And for instance, just to show you how fun it is, this is particularly useful, for instance, for Windows programmers. You can do Python m calendar, and you get a nice calendar, right? You can.
JSON.tool is another one.
Oh yeah, JSON.
JSON.tool.
Tool.
If you pass it any JSON,
Uh-huh.
it will parse it and show it. So
Nice. Very good. So
pre-printed.
very nice.
The way to find those is you search for modules that have done their main,
Yeah. Uh-huh. Yeah.
or have done their main .py file.
Mm-hmm. All right. Thank you. Site? Oh, site, this one? Oh, yeah, that's good too.
Very useful for debugging.
Yes. Yeah, totally.
And also web browser.
Yeah. Yeah. Anyway, so these are useful, and so you can run doc tests like that, which I just did, right? And but because it gives a lot of errors, in order to do the exercise, you probably want to run it by passing another option, which is the option fail fast. This will make it stop at the first error, so then the test will guide your implementation. You solve the first problem, and then solve the next problem, and so on. So this is the exercise. So what is happening here? Let me show you what's the problem. So the problem is, it's complaining about fidelity promo. And if you open the strategy exercise strategy, then inside there's strategy PY. No, I'm looking at the solution, sorry. Well, wait. Exercises, strategy. I seem to have, well. Okay, all right, this is the problem. The problem is that I am calling fidelity promo like that. And the naming convention suggests that, and also I'm not invoking it like I was before, because before I had to invoke the class because I need to instantiate a promotion in order to pass it as an argument to the order. But here, what we are going to do is, and you're going to be able to delete this import. Look at the comments here. So you can delete this import because we're not going to use the ABC machinery. You can delete this whole thing. And then you can transform these three classes into functions that have the names as described in the doc test. So instead of having a class called fidelity promo, I will just have a function called fidelity underscore promo. So snake case instead of camel case. And that's it. So basically, you're going to rewrite those classes as simple functions that implement the same functionality. Does that make sense? So I'm going to give you 10 minutes to do that. Notice how the promotion function is going to be used here. Right? Before we had self.promotion.discount, and now we only have this. Yes.
What was the dot test line?
Okay. Mm-hmm. It's this line. Yep. Very good question. Thank you for asking it. Yes, it's true, but maybe sometimes we get, uneasy about that. Are the tests actually running? So you can always add a -v option, which makes it run in verbose mode, and then it will show the tests that is running. However, I only recommend it just to double check whether the tests are passing, because it's actually nice in practice not to have any output, because when there is output, you know there's something wrong. Okay? So the -v option does that for you. See, if you run Python 3 -mdoc tests -help, it shows the options that you can pass. Although it doesn't say what the V stands for, we know it's verbose. It's actually 2 dashes help, and otherwise it complains that I gave too much information. Oh yeah, now it explains everything, yeah. So it's -v, -h to have a full documentation. Oh, there's also a shortcut for fail fast. I didn't know that. Maybe that was added later. That's nice. -f. Yes, nice. I'm going to get a refill of water. I'll be right back. All right. Who managed to do it? Quite a few. Yes, excellent. So let's get on. Who is partway through, but got some of it working? Yeah, the rest is kind of more of the same. Okay. So, basically, let me show you the code for the solution here. So what happens is we just have these nice functions. We don't need that self attribute, the self argument anymore, and we don't need the interface declaration. And so this is it. This is the best kind of refactoring, right? Throwing away code and keeping the functionality intact. Now, so why is it that we can do that in Python? Because in Python we can use functions as objects, and functions implement a standard interface, which is actually, if you look under the covers, is a special method called dunder call. So dunder call is the method to invoke and execute a function. So whenever you see a design pattern that has you implementing an interface that is made of one method, that's kind of a smell. This idea came from another language where functions are not objects. Because if the interface has just one method, you can replace it with a function and just call the function. Okay? And this happens with several design patterns. So in the Peter Norvig slides, there's a slide there where he says, if your language has first-class functions, you should rethink these patterns. So strategy is one of them, and there's others, command, and there's others. It's not always it's not always a good idea to replace a pattern like that with just functions, but in this case, it makes sense. So the first thing that you should consider is, am I forcing people to implement a class that has just one method? The second thing is, does the class have state? And in this case, the class has no state. So this makes it a really strong candidate to be a function, right? Curiously, even if there was some state, like for instance, let's suppose there was a certain promotion that had to do with the first orders of the day. The first 1,000 orders get this discount. So you need to keep a counter of how many times you've applied that discount, okay? But even then, because of the standard, because of the data model, you can implement this as functions in the common case like we just did. And if we need something that has a state, you could implement a class that implements the dunder call method. And instances of that class can be used as functions. Right? So whenever you have a class that implements dunder call, you can grab an instance of that class and invoke it as a function. So, yes. Another thing is, if you read carefully the chapter in the design patterns book about this chapter, they say an interesting thing is that the fact that you have to instantiate this thing here is unfortunate, because if you're running, if you're Amazon and you have millions and millions of orders, and you're applying that same promotion that has no state, you're still instantiating every time. But all the objects are the same. But that's the way the interface is designed. So they actually address that in the book, and they mention that that one possible solution to that is to use that pattern, the strategy pattern, with the flyweight pattern, which is a pattern that is used when you have many, many instances of some simple objects. So then you're piling up one pattern on top of the other. And a problem of design patterns in general is that they add flexibility, but they also add complexity. And in that case, to solve the problem, they are suggesting you to use another pattern. So things get out of hand. Like I said, it's not all. Some of those patterns are, make perfect sense in Python. And sometimes even one of these patterns that maybe in some cases can be simplified by the use of functions, sometimes it would be better to implement as a class for other reasons. So, but this is, okay, so let's talk about another feature that would be interesting to have in a system like this. So suppose you want to have a special promotion. I'm calling it the best promo. So the best promo is a strategy that applies all the other strategies to an order and returns the maximum discount available. Okay? So one simple way of doing it, the code is there, but it's just an addition of this to the code, to the solution of your exercise there. So what I'm doing is I have this promos is a list of several, is a list of references to the promotional functions. And then the best promo, like the others, like the other promotions, takes an order as argument. And then I iterate over each promotion in the promos list and apply that function to the order. So I get a number, which is the discount value, and I return the maximum value of doing that. Okay? So in this case, I don't even care which promotion it is. I just want to get the maximum possible value. Okay? However, this depends on that promos list. And that list has to be manually edited, which duplicates information in the code base and thus breaks the do not repeat yourself principle, right? So the problem is, imagine somebody implements a new strategy and forgets to add that strategy to this list, then you're going to have a subtle bug, because the strategies are going to be selected according to complex criteria involving the customer and the order structure. And so it may not be immediately obvious that that particular strategy that was just added is not being applied. So it's kind of a problem. So how do we solve that problem? There's a few ways of doing that. One way is to use a little bit of metaprogramming, a little bit of introspection. And what I do here is I put all the promotions in another file, in another module. And so these promotions here is actually the module that I import elsewhere in the program. And then I use this function, getMembers, from the inspect module. So the inspect module is there to help you do introspection, to help you gather information about the program, about modules, about functions, classes, and so on. And in that case, the getMembers function gets at least one argument. The first argument is the object, which may be any kind of object. It's smart about that. And it will return the members, which are the attributes, which may be just value attributes, data attributes, or maybe methods. And it will return that as an iterable of tuples, where each tuple has the name of the attribute and the value of a reference to the value of the attribute, which in this case are functions. And why are they functions? Because I passed the second argument to getMembers. So the second argument is a Boolean function that will return true when the object passed to it is a function. So it will filter the results that getMembers will yield to have only functions. So now, any function that is implemented in that promotions module will be used in the best promos, in the best promo function. Okay? Does that make sense? Yeah. Yes. Excellent question. And this is thank you for asking that, because this is the major failing of this solution. What if somebody put another function there that's not a promotion? So this will break horribly, and it's really a weakness of this solution that we're going to solve in the next solution. But I'm just pointing out here's the thing. Introspection in Python is much easier than in most languages. And you can leverage that to provide services to the users of your APIs. Like, for instance, don't have them repeat something if there is a convention. So the convention is put the promotions in this file here, and any function that's there, I'm going to use. So in the book, I actually discuss several solutions to this. One of them, which is a little bit hackish, but is a reasonable solution, is besides testing whether I further filter this list by taking only functions whose names end with _promo, for instance. Okay? So then you say, so then you put a comment saying, please don't add a function named something _promo if it's not a promotion. Okay? Can we agree with that? Right, so that's much safer. It's a bit hackish because it has to do with naming, but it's okay. I think it's better than this failing that you found that is serious, really, in this case. Okay, so the whole point here is really to create this list, right? The implementation of best promo didn't change a bit. It's just creating this list that is different. Okay, another option is to use a registration decorator. Okay? And so, how does that work? Here's the thing. Uh, when I was writing the book, I was always trying to find the simplest possible example to get started on a subject. And I was having a hard time finding a simple yet meaningful example of a decorator. Because usually when you study decorators in Python, the canonical example of a decorator is a decorator that returns another function. So that it wraps your function, the function that is decorated with something. So it changes the behavior of that function, usually by adding behavior to it, but sometimes doing other things. And that's, okay, that's the way decorators work. That's extremely powerful. But then after a while, I realized there are other kinds of decorators that don't do that. And many frameworks use those other kinds of decorators. Those are decorators that are called registration decorators. So what is a registration decorator? It's a decorator that doesn't change at all the behavior of the function that is being decorated, but it registers that function somewhere in some central registry so that it is going to be used for something. Like, for instance, some web frameworks use that you decorate views like that. You see, this function is a view. And that decorator may or may not change the behavior of the function, but the important thing is that it's registering the view as one of the available views so that the routing machinery can use that. Okay? So, in this case, what happens is, let's forget about the decorator first, how it's implemented. Let's look at how it's used. So this solves that problem that you just raised, because now I explicitly label functions that are going to be used as promotion with this decorator. Right? And how do decorators work? So one of the things that you need to understand when you're doing more of this dynamic kind of programming, more of this meta-programming kind of stuff in Python, is the way that Python reads a source code, a module. So it basically just reads the module once from top to bottom when it's loaded. Okay? And so if there is a def, like this, for instance, what is the result of running this? The result of running this is creating, in the global scope of this module, a function object called promotion, but it doesn't run the body of the function, right? It just defines this object and hangs it in the global scope of the module with this promotion name, okay? Now, what happens when you load code like this? When you load code like this, well, first of all, in order to be able to call promotion like this, or to use this decorator, this promotion has to be imported from somewhere, or maybe it's defined on the same module. But usually for decorators, they're not defined in the same module. They're usually part of some library that you're using. So you import that and you use it. So when you imported that, the decorator functions were defined, but they are not running. So this was defined. And this is the example. If you look at the code there in the repository, all of this is in the same source code, just for simplicity. But I separated them in two parts when I did this slide because I wanted to emphasize that usually these are not in the same place in your program. The decorators are defined someplace and used elsewhere. Okay, so when you actually use the decorator, what happens is, first, the interpreter defines this object, this function object, and then passes it as an argument to this function. So now what you get is this promotion function is called. And what does it do? It just appends the promotion to that promos list that starts empty and returns it. It has to return the function because even if we are not, because the thing is, the result of calling a decorator is to replace the body with whatever this decorator returns. So a decorator should always return a function. And most of the time it will return a function that has the same signature and the same type of return value. I say most of the time because not always. Frameworks, web frameworks use decorators that don't follow this rule because they are the ones that are going to invoke the function. So sometimes they change the return type, for instance. Right to, for instance, you return a string, but it's decorated as a view. So the framework knows, okay, he's using this function as a view, and he's returning a string. So what I'm going to do is I'm going to wrap this into a nice response object with all the machinery needed to produce a page out of this. Okay. So, but usually the decorator should return. Will always return a function. Yes, that's true. And it usually will also keep the same interface, meaning take the same arguments and return the same type of response or result. So in this case, I just return the promo function itself. Okay? Yes?
So the decorator actually gets called for everything that's decorated?
Exactly. So the decorator in this example is called twice. So it's going to be called as many times as it's used in the source code. Right? And the interesting thing is, now we don't need to have a convention that the module where the promotions are must be named this or that, or the functions need to be named this or that. The functions can be defined anywhere in the system as long as they are decorated. Okay?
I didn't understand why it needs to return promo. Why it needs to return.
Okay. The reason is that what the interpreter does when it sees a decorator is, first, it builds the function object. Then it takes this function object and passes it as an argument to this other function. Okay? And this function will, so the decorator will return another function, or in this case, the same function, it doesn't matter. It will return a function that will replace this one in the global scope of this module. So after you run this, this is a different example from the majority of decorators because it returns the same function. But if you decorate a function with another that returns a different function, if you inspect what is attached to the fidelity name in the global space, is not the function that you define there, but the function that was returned by the decorator. Okay?
So fidelity wouldn't be callable if you didn't return.
Yes, exactly. If this returns something that was not callable, then you're basically breaking this whole thing. Yeah. Mm-hmm. Yeah, so decorators are kind of a tricky subject, but I think this is an example that is simple yet useful of using decorators. Like I said, most decorators define a function inside here that does something else and returns that function to replace the function that was decorated. But this is actually doing something that is useful, but doesn't go as far. All right? So, let me do something here. I'm going to demonstrate this because I think it's useful. So this is now my favorite Python console. Jupyter Notebook is awesome. And so I'm going to do a function that is called log f. And what it'll do is it's going to do Okay, so we just defined a decorator, and that decorator. So let's use it. So I'm going to define a function called double that returns n times 2. Whoops. Sorry. This doesn't understand English. So, okay. So now, if I look at double name, it's inner. And what is happening now? Let's run it. Double tree, which is actually the name of a hotel, right? Yeah. Anyway, so this is the result of the print over there, right? So this proves what I was saying, that this syntax has this function replaced by whatever the log function returns. And the log function returns this inner function, which does something else and runs the function that is being wrapped. This is usually the behavior of most decorators. It does something before or after the decorated function, and then invokes the decorated function so that the functionality that the user expected is intact, right? Yeah, so that's the common. So if you don't, this is actually, this is the way it works, but it's not very convenient when people are debugging. For instance, they don't want to see this inner name in all of the decorator functions, right? So because of that, there's a wraps decorator that in the Python functools module, I think it is, that you can actually decorate this inner function so that it will copy the name. It will change its name to be the same name as the function decorated. And we also do some other things that are nice to do so that people don't get confused by this change.
I have a question about the args keyword.
Yes.
I understand that that's in the namespace of the log, and it tells you the arguments that are passed at. Why is it not showing any arguments of log, like the caller of logs, whatever the argument is? Why is the arg showing that? It's showing the arguments going in.
Okay. Well, because, so remember that the double function was replaced by the inner function, right? So when I pass 3 here, this is the first value of my star args. That other argument, f, is only comes into play here.
Okay, so if I call args right above def inner, it would just show that.
No, it wouldn't, because above inner there is no args. Star args is not a magical thing in Python. It's just args is a name that I can. It's any name. The fact that it has a star in front just means that I'm going to accept an arbitrary number of arguments.
So that could be called
Anything, yes. Yeah. So it's not like a special variable that, I think in JavaScript there is that, right? There's an array of arguments that you look at. No, there's no such thing in Python. Okay? Oh yeah, this splat operator. Yeah, yes.
To add that the double dot underscore underscore name
Yeah.
is also a very big problem with the docs.
Mm-hmm.
If you call
Exactly.
for that,
Mm-hmm.
it will also return for the inner, which doesn't have.
Yes.
So what I would say is there's a very nice set of blog posts by Graham Dumpleton,
Totally.
and there's a library which is a compilation
Yes.
as a result of those posts.
Yes. Yes. Very good tip. Yes. So yeah, I actually cite that in the book. Graham Dumpleton wrote a series of blog posts which mainly say, basically, you're doing decorators all wrong. This is how they should be done, and it's kind of complicated to do it really properly, to work in all the different corner cases that he found out, and then he implemented this library called wrapped. So yeah, one of the things that you will find in my book is that I cite a lot of people, like more than 100 people. And so most chapters have 2 pages of references, and I really did try and anything that I found that was useful. And Graham Dumpleton certainly is one of those people. In the chapters about decorator, I mentioned him. Yep. All right. So I hope this clarified how decorators work for those who haven't seen it yet. And so let's go back to this. So our decorator is much simpler than that one because there's no inner function, because we are not changing the behavior of the function, we're just doing something with it. In the case, we're just appending it to the promos list there, right? So I think that's the best solution I found in the book to this problem. So now, because we have time, I'm able to go back and talk to you about the bonus section of because our lunch is 12:20, they tell me. So let's go back to the hashing part that I skipped previously. Now we are back to the vector domain, okay? So what is the thing about hashing? If I want to be able to use hash or vector instances in sets, I want to create a set of vectors, then I need them to be hashable. And also the same requirement applies if I want to use a vector as a key to a dictionary, right? And so let's see how to implement hashable objects. So an object is hashable if and only if its value is immutable, and that's critical. And so are tuples hashable? It's a trick question. Yes? The best answer here is the consultant's answer. It depends. Why is that? Because tuples are immutable, but their values may not be. That's tricky. Why is that? Because a tuple can contain a reference to a mutable object. You can actually have an item in a tuple that is a list, and if you change the value of that list, then you're changing the value of the tuple as well. Even though the tuple is immutable, what is immutable about it is only the fact that the references it contains when it's created are never going to change. They are always going to point to the same objects. But if one of those objects is mutable, then what you have is actually a mutable tuple in a way. The value of the tuple is mutable. So that's the problem. I would say it probably would be a good idea if Python refused to accept mutable items in tuples. Maybe they could check that and have raised type error if you try to put a mutable object inside of a tuple. But anyway, so the value has to be immutable. The object has to implement dunder hash. It has to implement dunder EQ. And this must hold always, that when 2 objects are equal, their hash is also equal. Okay? So, in order to make this true, you usually have to implement your dunder hash to use all the attributes that are also part of the comparison with the dunder EQ. Does that make sense? Does that make sense? So if dunder EQ takes into account certain attributes of the object when it's doing the comparison, those same attributes must also be part of the hash computation so that this can be true. So the basic algorithm to compute the hash of an object is to compute the hash of each of its attributes and then aggregate those hashes in some way. And usually the way to do it is using the XOR operation, the bitwise XOR, because hashes are integers, so you can XOR them together. And so what I'm showing here is that I am computing the hash of the vector using the hash of the components. See? So the hash of the V1 equals the first component XOR the second component. The hash of this is the XOR of all the components again. Okay? It just so happens that the hash of small integers in Python are the integers themselves. So I can do that. I can do this demonstration. I can't do it with floats because the hash of a float doesn't look anything at all like the float, except when they are the hash of round floats, because of the requirement that 3 equals 3.0. So the hash of 3.0 must be the same as the hash of 3. So Python does that. But anyway, so what I'm showing here is that the hash of this is equals to the hash of this, XOR the hash of that. And the implementation is actually a very good demonstration of the MapReduce coding pattern, where the map stage takes a sequence of values and returns a new sequence of value transformed in some way. And then there's a reduce step that aggregates all of those values into a single result. And this is how I did it. So what I do is, again, with a generator expression, I compute the hash of each component of self. So now I have this generator that will yield all those hashes. And then to apply the XOR to all of them, I use the functools reduce function. Okay, this was, in Python 2, this was a built-in function. Now it was demoted to the functools module, because this is to encourage people to use some reduce functions that are already in the built-in functions and that a lot of people don't know. For instance, sum is there, all and any. All is a reducing function that will return true if all of the members of the iterable are true. And if one of them is not, it shortcuts, so it's very effective to verify that you have a bunch of non-empty things, for instance. And there is also any, which is the opposite. So it returns true if any of the elements is non-empty or is truthy, which means, like for collections, which means that if there is anyone that's not empty. So anyway, there are those built-in functions that are very nice and that solve many problems that people used reduce to solve before. And now if you want to do something different, you can use functools reduce. And also because the Python community doesn't love the lambda construct, we also have this nice module called operator module, which implements all of the language operators as functions so that you can use them instead of a lambda. what makes it less readable? Yeah, well, yeah. It's, sorry? Yeah, what uh-huh. I've been using Python for 18 years, and I have always found Lambda a little bit unreadable. Yeah, so I prefer to use this, because, so yeah, I'm passing this short function instead of defining it. It would be easy to define with Lambda. Yes, it would. But, yeah, this is a matter of opinion, really. I know. Yeah, go ahead.
There's convenience to having that instead of lambdas, and it is that operator.xor will always have the same ID. Whereas if you define a lambda, it will be basically an anonymous object that will be created on the
Every time.
where you call it.
Yes, it's true. Yeah. Mm-hmm.
Do assertions, and you can do basically lookups for this.
Yeah. So his comment, did you hear his comment? Yeah. So yeah, you're not creating all of these functions on the fly. Yeah. And here's another thing. After playing with, actually not playing, but I had to work with Node in a project recently, and I did not enjoy it. And I have to say, anonymous functions have a grave defect. They don't have names. So when you're debugging, it makes it harder because, this thing is identified by this X number, so, yeah.
Why is it so prevalent in Pascal?
Well, of course, so the thing is, Python is not really a functional programming language. It has some traits of functional programming languages, mainly because way back then, Guido decided that it was a good idea to have objects, to have functions be objects, and once you get functions as objects, you can apply many patterns from functional programming. But it was never intended to be a functional programming language. And I think the problem with the Lambda is it doesn't fit very well with the language syntax. It's very limited. You can't do statements. So yeah.
And then you also have, so instead of a lambda, you could just define a function.
Yes.
So you can, like, inside where you would do
Yeah.
something equals lambda something,
Yes.
you just do def in there, and the def would have that scope. So
Yes, this would be a way of doing solving the syntax problem. But then you would have, for the first time, sort of an expression inside another, a statement inside an expression. And the syntax of Python is statement-oriented, which is less flexible than expression-oriented syntaxes, but is also more regular, so it's easier for beginners. And I think is one of the reasons why Python was so successful among people that are not professional programmers, like physicists, because it's more approachable because of the regular syntax. Anyway, so basically what this does is, the reduce function, what it does is, it takes the function, it takes a function as an argument, and then the second argument is some iterable, and the third argument, which is actually optional, is the initial value. In this case, it's necessary, because the initial value by default is none, and it doesn't help with us here. So in our case, what it does is, it takes the first of the hashes that we just computed here, and shores it with 0. And then the result of this shore is held in memory, and then it takes the next hash and shores with that result, and then the result of that is hashed with another one, and so on and so forth. So it consumes all the hashes by applying this shore operation, and then what you get is a single number at the end. So because it's a reducing operation, that's what it does. So now here I did this just to prove that I can create a set with 4 vectors, and it works. Python would complain if you try to create a set with something that is not hashable. So, yeah, that's... Any questions about this? Yes?
Is the object as such hashable, the class?
I am not sure. The thing is, I think the hash of object just returns the ID of the object. So then and the object itself, well, you know, object itself, we don't usually, why do we use instances of objects in reality? When is it that we use instances of objects? One way that I see is as sentinels, right? You instantiate this object, and I call it sentinel, and then I put it, and I yield it, for instance, in some kind of generator to signal that this is the last thing that I'm going to, something like that, right? And then, so the person who is using my API knows that if there is this sentinel and those objects, they compare equal, and no other thing will compare equal because the implementation of dunder EQ in object just compares the IDs, right? So I'm not sure if they are hashable, actually, but we can actually test this really quick by just trying to do a set of objects. Yes, it's hashable. Yeah. Yes, so and every object is different, right? So. See, those are two different objects. Yeah. Okay, so that's pretty much what I had to no, I have some wrap-up slides, and then we can have Q&A and go for lunch. So, wrap up, considering how to make Pythonic APIs. Ideas to consider. You should study well-designed packages from the standard library and from the Python package index, like requests and PyPy. Implement special methods from the data model to emulate the standard behaviors your users expect. And like, for instance, if here's a thing that I failed to mention. If you're doing an infix operator should never change their operands, ever. This would be really evil if you did that. Okay? What they have to do is compute a new object that is going to be the return value. Okay? So you can leverage first-class language objects, functions, modules, classes. Like, so for instance, okay, so that solution to the best promos, the first solution, had some failings, but it's an interesting solution. I have this convention that if I have a module named promotions, every function in there is going to be a promotion, so I can introspect that and do this automatic thing so that the user of my API doesn't need to remember to copy those names into a list, right? Also, if you start to think about classes as objects, then the factory patterns, there are some standard design patterns with factory in the names. Most of them become useless once you consider that in Python classes are objects, are live objects that you can actually invoke at runtime to create a new object, a new instance, and so on. And with great care, I put this a little emphasis here, because metaprogramming can be a door to shooting yourself in the foot. But do some metaprogramming to reduce boilerplate code that your users would need to write. And review slide 20 of this presentation, which was typical characteristics of idiomatic libraries. There's some other items like this that I put after I showed you the request in the PyTest library. And this pretty much wraps it. I just have two announcements to make, and then we can have questions and go for lunch. So the first announcement is there's going to be a book signing. Already brought a bunch of my books here, and if you get in the line, they're going to actually give you a book for free. I think they have 20 books to give out, right? And this, I'm confused about the time, really, because we agreed that it was going to be at 10:30 on Tuesday, but then they sent me an invite for 12 or 12:30 or something like that. So I just noticed that, and I asked them, what is the real? So I suggest, if you're interested, that you go at 10:30 to the O'Reilly booth and ask when it's going to be. Anyway, so that's going to happen. And also, please evaluate this tutorial. It's really important, because I don't know if you know, but you know, this conference is extremely competitive. I submitted several. I've already talked at PyCons before. This year, I submitted several ideas for talks in this tutorial, and I made it with the tutorial, so I'm really happy. And but yeah, please evaluate, because this can help in the future. And yes, so I work for ThoughtWorks. ThoughtWorks is an amazing company to work for. I suggest, I think maybe they're going to have a booth here. I'm not sure. But come talk to me if you're interested in knowing how it feels like working for ThoughtWorks. And that's my corporate email. And yes, questions, suggestions. Yeah, sure. Yeah. So the slides are already at SpeakerDeck. You know, speakerdeck.com is another place, not SlideShare. SpeakerDeck, speakerdeck.com, and my account there is my last name. And my last name is pronounced Ramalho, which is a kind of a nuisance here in the US, because I say Ramalho, and they go straight to the age, of course, right? And I say, no, yeah, it's Ramalho, but it's spelled with an R. And yeah, so Ramalho at SpeakerDeck, I put them there, the slides, and yeah, go ahead.
At some point, you use none for a default value in the strategy portion, and I'm wondering what your thoughts are on using none as a default value and detecting that versus using like a basic singleton value that just
Mm-hmm. Oh, yeah. Yeah, so the question is, if I use none as the default value for an argument when we implemented the strategy, and his question is, how about using some other special value? It depends on the situation. I think sometimes it depends on whether whether none would be a reasonable value for that or not. You know? In that case, if the person is passing none, it means, okay, they don't want to provide a promotion, so okay. So it's the same as the default behavior that I need. But if none is a useful value for people to pass, which would mean something, then yes, I would suggest you do some kind of object, special object, and that's why you use, you instantiate object like that, you know, I don't know. My crazy value equals object, open close paren, and then you put my crazy object there, and if it's that, then you know it must be that. Yeah. Somebody else raised their hands back there? No? Yes?
Outside of the examples that you already gave, what are some of your favorite standard libraries as far as
Sorry, I didn't understand the question.
So outside of the examples that you gave, what are some of your other favorite standard libraries that like exhibit these qualities?
Oh, okay. For instance, Flask is really very Pythonic in the way it does many things, and so it leverages more language features to be. And yeah, the thing is, there's sometimes people question whether you should or not leverage so many language features, and so because sometimes if you do that, then you're alienating people that are new to the language in a way. But let me show you a quote that I put in the book that pretty much convinced me that that's the way to do it, which means which means really leveraging the standard library or the language features. Yeah, so I found this, and I actually used it for the first quote in the book. My computer is a bit slow, but yes. So this is the quote. I put it in the preface. Right? Yes, so go for it. Learn the language. The thing is, the language is an amazing set of conventions that if you follow and your colleagues follow, then you have a more powerful way of communicating ideas, you know. If you get satisfied with somebody, who was it that said something? Yeah, you said it, right? That
Dictionary.
yeah, and what was the point that you made that was really good was
Not all one.
no, but there was another point. The point was that yeah, okay. So if you don't follow the language conventions, or you decide not to implement this because this would be magical, then what you are doing is you're forcing people to come up with their own solutions, and people will come up with different solutions to problems that are already solved in the language. So I think it is worthwhile to spread this knowledge in your teams and use more of the language features, because it's a standard way of doing things. This is the main thing that is bothering me about Go, is because they decided to go for a language that has excellent concurrency. That's really incredible, amazing, and that's the reason why the language is successful. But from the abstraction point of view, it's very low abstraction. So you see yourself coding similar things over and over, and you're wondering, you know, what is the best way of doing it? So if you don't have a standard way, because of the language works as a framework that encourages you to do things in this or that way, and that provides abstractions, then you're pretty much coding some things over and over and again, and then you need to complement that with an amazing coding patterns repository. That's something that's missing. You know what I mean? Like, for instance, there's no set type in the standard library of Go, and because there's no generics, you pretty much have to redo a set every time when you do. And if you start using sets in Python, they are, you know, incredible, because Boolean logic and set theory have a very common core. And so when you use set, you simplify a lot of logic, right? If you use sets in Python, you know that, right? And so you go to Go and you don't have a set type, and you have to, and then you go on the web and you find the different implementations. But if you adopt one and another part of your company, they adopt another one, then they're using different sets to do, you know. So anyway, I think this is a very good point that Tim Peters made. He's also the author of the Zen of Python, and so, yeah. All right. Folks, thank you very much. It was wonderful to present to you this morning. I hope you enjoyed it.